Hello, everyone. I'm Professor John Aubert, and I want to welcome you to the very first meeting of Introduction to Weather and Climate. And we're going to jump right in. I want to also make a point that every single lecture video that I do is accompanied by a set of lecture notes, which I've made available to you in hard copy. I've made available to you posted on our Canvas site. So please keep that in mind. Now back to this picture, it's always astounded me. This was in the late 60s, one of the first passes very close to the moon, where we got all the way to the moon and spent the equivalent of billions of dollars and lost lives. And once we got there, what were we fascinated by? We were fascinated by looking back at Earth. It is something that fascinates us. And that the central topic of this class, of course, is the atmosphere, weather, climate. Well, we want to answer some of the basic questions. What are the differences? Yeah, let's jump right in. What I commonly like to say when we talk about the difference between weather and climate is that weather is what you get and climate is what you expect. So you can see some definitions here. Weather is the state of the atmosphere at a given time and place. What does that mean? Well, is it raining? Is it snowing? Is there a heat wave? Is there a thunderstorm at a given point in time? That would be weather. Climate, on the other hand, is the long-term average of temperature, precipitation, or other measurable variables. So, for instance, it could be cool and rainy on a July day in Sacramento, but climate says that is highly unlikely. The long-term average says that it's more likely to be dry and warm. So let me take you to some of these slides. This is really an example of weather. This is a weather map, so it is saying where in the country it's snowing, sunny, cloudy, raining. Again, the state of the atmosphere at a given place in time. Climate, on the other hand, as I said, is the long-term average. So this particular graph shows for a given location, this is New York City, and this is from your textbook, monthly average temperatures. So what is the average low, what is the average high, what is the average temperature. And usually when you hear people talk about average temperature for a given location like July in Sacramento, that's actually 30 years worth of data. That's if they say what's the average temperature for July in Sacramento, they take the average temperature for every single day of the month for 30 years. So that's almost 900 variables just to get that one number. So we're going to work with this continually. We're also going to talk about climate change, certainly. The next and let me also say is meteorology is the term, but it's a more formal term for the study of the atmosphere, the study of the processes that take place within the atmosphere. It's the study of what we would normally call weather. So it's kind of actually an old-fashioned term, originally meant to be the study of meteorites, but that is no longer what it means. So another basic question, why care? Why would we even want to study weather? Well, it has such an incredibly important impact, not only on our daily lives, but on our livelihoods, on the economy, ultimately on our survival as humans. So we will come to find out that weather is deeply impactful to humans, not just on a casual day-to-day, what should I wear to school or work basis, but really fundamentally on society. This graphic right here lists the economic impact of severe weather. And, and it, in this case, is talking about the total number of events and the monetary value of the damage. Again, weather can really deeply impact humans and our society negatively. So this is just an example of that. So let me go back to the notes for a second. Um, what in fact is science and scientific inquiry? I want to do just a really brief primer on what science is, what it isn't, what some fundamental terms are. We're not going to go through the entire scientific method. I have a preferred approach that I like to bring up. Um, really, it's about, I like to say, it's about asking and answering questions, but doing it in a particular and structured way. We do some form of science every day, but I wouldn't necessarily call it formal science. But we look around at the world and we make observations and then make decisions based on those observations. So in science, what is a hypothesis? It's essentially an educated guess. It says it can be stated as a formal statement, like my example here is clouds are composed of small liquid droplets, or as a question, is a cloud composed of small liquid droplets. Hypotheses are always based on prior observations, but science tries to either prove or disprove a hypothesis by making observations, by collecting data and information. So, and a hypothesis has to be testable, and we'll talk a little more about that in a minute. Theory, on the other hand, and you hear people commonly use this term, and you hear people often will say, oh, that's just a theory. Well, let's be clear, in daily usage, it can mean conspiracy theory, all kinds of crazy things that people believe. But that is not how scientists use theory. Theory, it turns out in science, is an incredibly strong word. It really means a set of ideas that are incredibly well supported by observations and by evidence. Now, when we go through notes like this, I'm not going to read these word for word. I'm going to paraphrase. I'm going to sometimes simplify. You, just to be clear, need to read all of these word for word. One interesting thing about scientific theory is that it is often what we call predictive. So good scientific theory will tell us essentially about the future. So a classic example in science, if we look at the theory of climate change and anthropogenic human-caused climate change, contrary to what many people say, the scientists have been predicting numerous outcomes based on what we know about human-caused climate change for years, that it will be warmer, that glaciers will shrink, that it will have an impact on plants and animals. And all of those predictions, to one degree or another, have come true with quite good accuracy. And again, you don't necessarily normally hear this in day-to-day speech. So hypothesis is an educated guess that we then try to test and collect data on. And theory, again, is a very strong term in science, meaning basically a scientific explanation that is incredibly well supported by evidence, and that is often predictive of something that will happen in the future. So I want to touch on what I call the rules of scientific inquiry. These are paraphrased from a lot of different sources. So this is not what, quote unquote, the scientific method, but let's take a look here. This is an example from your textbook, and it's an instrument package of all sorts of instruments that collect data about the atmosphere, that collect data about weather. And this is science, making observations using a regular process, collecting information. This, on the other hand, flat Earth, is not science, but there are many people out there who try to use science to quote unquote prove the flatness of the earth. Now, I'm not going to get into this in any great detail. You can go look this stuff up yourself. It is absolute and complete and utter absurdity, but there are people who have somehow convinced themselves of this truth, and they think they're using science. Well, let's take a look here. What are the quote unquote rules? First of all, observation must come before conclusion. A lot of people try to prove their beliefs using science, and that's not how it works. Science tries to ask questions and then make observations about the world. So that's where the hypothesis comes in. You must follow accepted science. So scientists basically come to broad conclusions about what is and isn't true. So you can't suddenly, in your scientific inquiry, invoke magic or miracles to explain something that happened. And I'm not dissing magic or miracles at all, but that is not science. Must be repeatable and verifiable. You have to be able to show others. Generally, formally in science, where scientists publish their work, put it out there for others to comment on and to evaluate. There aren't supposed to be secrets. You can't just say, we did this and this is how it is, and we're not going to show you anything. It has to be it has to withstand scrutiny from the outside. So repeatable and verifiable. Scientists must absolutely be willing to change their mind if they're presented with new contradictory evidence. So if you, and I have spoken with very, very strong believing flat earthers, and you can give people all of the evidence in the world and they won't change their mind. They'll simply change the topic. They'll try to do other experiments. So this is really tough for scientists, especially somebody whose life's work has been proven to be wrong. But this is fundamental to science. And science continually asks new questions. And there are some people who conduct science whose only goal is to disprove something. So when we talk about climate change, for instance, anthropogenic human-caused climate change, there are groups out there whose appear to conduct science, but the only thing that they are interested in is trying to disprove that humans are a key factor in what the current warming that we see, which is just absolutely untrue. Science asks new questions. It doesn't constantly dwell on trying to disprove things. So that is our first little video. This is going to be one of two videos on the introduction. And keep in mind, the introduction in this case is going to take place over two separate modules. So in this first module, we will have two videos. We will pick up on Earth systems science in our next video. Thank you for your valuable time. And again, welcome to Weather and Climate.